Log on, tune in, find out. Another good idea from Cambridge.
All right, thank you. So today I would like to present a large class of examples of these moduli, compact moduli of pairs, which are predicted by the minimal model program. Their existence is predicted. And here, there is a very concrete example, I think very easy to work with, very elementary, and it sort of comes for free in a way. I will explain. But before I do that, let me talk a little bit more about this prediction of the minimal model program, because last time it was a bit rushed. So I would like to say a few more words. So first of all, we have these properties of moduli functors. And there were some properties, 1, 2, 3, 4. So I would like to add one more, number 5. And it's called properness. And so here's the situation. So first of all, let's say S is, that's what S is. It's a smooth curve, or could be a speck of a DVR. So as we know in algebraic geometry, speck of a DVR is an ideal version of a little germ of a smooth curve. And then we have 0, a point here, and S0 will be this open curve where I remove the closed point. So this 0 on a DVR, that's a closed point. And let's say we have families of our favorite varieties over S. So some kind of family. And of course, we can restrict and get a family over S0. Just remove the central fiber. Now, this property of properness is, the question is whether we can go back. So if we start with some family here, so if we start with some family x0 to S0, does it come from anything? Is it a restriction of some family over a complete curve? And then the definitions, now in terms of moduli, what do we have here? So this is M of S0, and this is M of S. So these families moduli an isomorphism. That's how we denoted them. It's the values of our moduli functor. OK, so two definitions here. So if for any x0 to S0, there exists at most one extension, then we say that M, this moduli functor, is separated. And if so for any family, there exists exactly one extension after a finite base change. So this is S, and this is S prime. So we're making a ramified base change. So if this holds, then we say that M is proper. And of course, you recognize what these things are. These look awfully similar to the evaluative criterion of separatedness and properness. So the corollaries of this property are as follows. The first corollary is that if the moduli space exists, so if the moduli space M exists, then it is proper. Or, if you have this weaker notion, then it's separated. And the second second corollary is that if M is constructed as a quotient by a group action, or as a quotient by an equivalence relation. So R is this groupoid. So groupoid is just another word for a pre-equivalence relation. So remember, in this method, which I said is the most convenient and the easiest to use, that method of construction, number 4, using Kilmore. So there you have to check some conditions on this groupoid, on this equivalence relation. And once you have this properness, then the implication is that this group action, if you work in this version, or this equivalence relation is proper. And if also you have finite automorphisms, then it is finite. So finite means proper plus quasi-finite. So this is a very nice property to have for these two reasons. If you can construct your moduli space, then it will turn out to be proper, compact. But it also helps you to construct the moduli space. So then this theorem of Kilmore is applicable. So you can just plug it in. So this is one of the ingredients to plug in. Now, the connection with the MMP was the following. So MMP, let me be careful here and say exactly what the right words are. So MMP for log canonical pairs, I will define this today. But MMP for log canonical pairs in dimension d plus 1. So that implies that the functor of stable pairs xb, and remember that stable pair I defined by two conditions. First, there was a somewhat mysterious condition on singularities, which said that this is a SLC, semiabelic canonical. And the second condition was that kx plus b is ample. So this functor is proper. So this moduli space, if you can construct it, it will end up to be compact. It will be a compact moduli space. And also, as I say, it helps you to construct it. So once you, let's recall what those properties 1, 2, 3, 4 were. Once you work with polarized varieties or pairs, and here they are canonically polarized because you already have this intrinsic ample polarization, k plus b. And what was number 2? Number 2 was boundedness. So once you know that you have a bounded family. And number 3 was automorphism groups have to be finite. That comes for free. That's implied by those conditions. In number 4 was local closedness. And so local closedness of the functor, that's a hard part. That's a delicate part that has to be dealt with very carefully and really tricky. So Friday,
What does that uniqueness statement mean?
Let me say again, if you start with the family here, and you ask, is it a restriction? And so you say that your functor is separated if there is no more than one restriction, 0 or 1. And you say that it's proper if there is a, if it is a restriction of a unique guy here, possibly after a base change. So these finite base changes come because these pairs have finite automorphisms. They're finite, non-trivial, possibly non-trivial, but finite. And so there is some finite monodromy. You have to get rid of it. So you go to a finite base change.
The base change is not unique.
Certainly not unique. I mean, once you kill that, the condition is to kill that finite monodromy. So once you killed it, any finite cover over that will be fine. But this is the difference between fine moduli spaces and coarse moduli spaces. So for a fine moduli space, here I would say there wouldn't be any base change. I would just ask for a unique extension. And for coarse moduli space, this is never possible because of automorphisms. And that's the best you can ask.
Do you require S to be separated?
I mean, this is stronger, right? The second condition is stronger than the first. So I gave two definitions in one. Huh? So properness is really what, but there were two in one. The second one was the important one for me. So that's the idea. This is what MMP does for you. And the idea here is, what is the idea of the proof? I sort of ran it for curves last time, but what you do is you use the log canonical model for a semi-stable reduction of a one-parameter degeneration. So this is d plus 1. Where is d? So d is the dimension of x. So you have a family of d-dimensional things, d-dimensional varieties, and you look at this total family. It now has dimension d plus 1. You choose a nice model, which is semi-stable. So it's non-singular, say, and the central fiber is reduced, normal crossing. And you apply this minimal model. You find the canonical model of this. But you do it relatively over S. So in the minimal model, there are some steps, there are some contractions, flips. You only do it in the fibers. So you don't do anything horizontally. So fibers. So one say that some people say it's dimension d plus a half. So I think that's quite official. So it's easier than doing it for an arbitrary d plus 1 dimensional variety, because you do it for already a fibration. So this. So when is this MMP known? So MMP known. It's really in the version that this version of MMP in the dimension d plus d plus a half. Okay, it's known for when d equals 2, so d plus 1 is 3, for threefolds, and has been for a long time, so for 15 years or so. And unfortunately, that's it. So there are these exciting recent developments in minimal model program, but they are not for log canonical pairs. They are for KLT pairs. So it gives something. It gives a weaker statement. So you have to put some more restrictions on the pairs. That theorem, the famous theorem that was proved for a finite generation of the canonical ring, it's for KLT pairs, not log canonical pairs. Okay, so that was it. So now we have a prediction, and we do believe MMP in all dimensions, so there should be this nice moduli space, and it should be compact. And then there is even a method of proving that it's really a projective scheme, not just an algebraic space. Okay, so now what I want to do is I want to show you this very easy example. I think, it's easy once you get used to toric varieties and playing with them and working with them, and then it's really elementary. So stable toric varieties. Before I get to that, let me define these little things: LC, SLC, KLT. So if you haven't seen them, it's a standard definition that I must give. So let's say what the standard singularities in MMP are. So there are. I'll stick to these three: LC, KLT, and SLC. And there are more. I will not need any more. Really, I will need these two. That's what I care about. Okay. So first, let's say you have a pair, AX, B. This is a variety. These are divisors. BI are between 0 and 1. They're rational numbers. And then I want to define one of these conditions on singularities. So first assume that that X is normal. Okay. Let's make this restriction. And then we have the codimension of the singular locus is at least 2. So therefore, we have the canonical class, canonical divisor, well defined because we can just remove codimension 2 subset, and then it's a non-singular variety. So there's canonical divisor. It's a Bail divisor. It's not necessarily Cartier, not necessarily given by some equation locally, but we have a Bail divisor. And then if we're in characteristic 0, as I hope we are, we can find a resolution of singularities, a nice one, so such that the union of these pre-images of BI and also the exceptional set. This is a simple normal crossing divisor. So there is some divisors here. We resolve, so now everything's not singular and simple normal crossing. So then we will assume that kx plus b is Q Cartier. That means some multiple, first of all, is integral. We can do that. These are rational numbers, so just clear the denominators. But also, I want this multiple to be a Cartier divisor, so given locally by one equation. So assume that, and then we can write this magical formula. We can Cartier divisors can be pulled back. You just pull back the equation. And what you will have a similar formula for ky and pre-images of divisors B. And then there will be some extra stuff. There will be some exceptional divisors. And then one says that this pair xb is log canonical if these coefficients at most 1, all of those, all the coefficients here are at most 1. And log comes from, this reminds you of a logarithm, Derivative of a logarithm is 1 over x. So these are no more than logarithmic poles. And then you say that it's KLT. So LC stands for log canonical. And KLT, this is Kawamata log terminal. This is if BIs are less than 1 and EJs are less than 1. So that's the condition. So even better. So like I said, these recent advances for in minimal model program, they're really for KLT pairs. And so that rules out the coefficient 1, for example. That's a pretty serious restriction, but something. There was a question. Huh? Okay. Uh-huh.
This definition doesn't mean I cannot run the minimal model program for X not normal.
So there's minimal model for LC pairs. There's minimal model for KLT pairs. Minimal program is a program, right? It's like a conjecture. And then the question is, when is this conjecture a theorem? It's a theorem for log canonical pairs of dimension up to 3. It is also a theorem for KLT pairs in all dimensions if K plus B is big, say, has many sections. But so there are all these versions of MMP.
Yeah, probably my question was, how will you solve if your variety is not normal? Can you just take the normalization and try to?
So that's coming up. That's coming up. So that's I'm about you. You're like 1 minute ahead of me, maybe less. So now assume X is not normal. Not normal. And so what can we do? And why do we care about non-normal? Because stable curves are non-normal, right? So for these moduli, we need at least stable curves, so we need some non-normal varieties. So that's the SLC definition, and here's what it is. First, we assume that X is S2. S2 is a CR condition 2. So for those of you who have a good background in commutative algebra, you know what this is about. In any case, these days we can just assume that we can just stick to Cohen-Macaulay, really. So there is a fairly recent result of Kohler and Kovac, and so what they prove is that in these SLC families, being Cohen-Macaulay is an open and closed condition. So these the part where your variety are Cohen-Macaulay will be connected components. So really, you can just ignore non-Cohen-Macaulay. Just stick to Cohen-Macaulay. That makes it easier for many reasons. Okay, so assume at least that, and assume that generically in codimension 1, X is nodal. Okay, so we want for curves, we just want nodal, and for say surfaces, we want something. It may have in codimension 2, it may have worse singularities, but in codimension 1, it's generically somehow looks like a nodal curve. All right, good enough. And of course, we want these divisors BI not contain any components of double locus. So there are divisors here. And the divisors sort of look like this. So they do not contain this double locus. Right? Then we can normalize. And on the normalization, there will be your divisors again, and we will include this double locus with the coefficient 1. So we say that the pair XB is SLC if the pair X nu, so that's the normalization, and then B nu plus double locus if this is log canonical. So this is the definition for the non-normal case. And where it comes from the analysis of that construction, of that situation. So I should say that this was first done by Kohler and Shepard-Barron in a paper in 1989. This idea was applied for two surfaces without boundary. It's a very natural idea, so it's quite old by now. And then one has to analyze. So they introduced this notion, SLC. And that's how you can define it intrinsically. So this is the prediction, okay? The MMP prediction. So finally, let's do something easy, I hope. So let's go to toric varieties.
Just a question about this prediction.
Uh-huh.
If you start with some surface without boundary, you have to add things with boundary and then in the boundary of the modified space?
No, it's an easier case. I would say technically it's easier if you add the central fiber in your one parameter family, if you add the central fiber with coefficient 1. The reason for that is the adjunction formula. Adjunction formula says that K plus E, restricted to E, is the canonical class of E. So for that adjunction formula, it's technically a little cleaner, a little easier to add this central divisor. But really, they did it, Kohler, Shepard-Barron did it without boundary, and then it's MMP for smooth varieties. So the end result has terminal singularities, canonical singularities. It's a bit easier, but not much.
So what MMP is finding a minimal model for each of these?
MMP, here's what MMP says. Yeah, let me say what MMP says. What is the MMP that I need? What I need from MMP is that the canonical model exists and is unique. Uniqueness is easy. That's kind of a trivial argument. Existence is the hard part. Existence is equivalent to saying that canonical ring is finitely generated. So this is a conjecture, proven in some cases, but not in all cases. So the general case is fairly equivalent in the log canonical case, is fairly equivalent to this abundance conjecture. And this is sort of the main remaining conjecture in MMP, in minimal model program, the abundance. So once abundance is proved, then everything here will be great. You can this will not be a prediction. This will be an actual theorem. All right, let's get to combinatorics. So let me start with toric varieties and MMP. So toric varieties. There are general toric varieties. These correspond to fans. So these I don't care about. Okay, these are unimportant for what I'm going to talk about. What I will care about is the projective polarized toric varieties. So you have a projective toric variety, and moreover, it comes with a polarization, so an ample line bundle. So these I will consider. And so what toric geometry tells you is that these are in a bijection with lattice polytopes. So there is, first of all, there is a lattice. This is a character group of your torus. And then, so it's an actual lattice. Lattice means just free abelian group of rank R. And then lattice polytope means it's a polytope with integral vertices. And then every polytope corresponds to a pair like that, and vice versa. For example, this is a P2 with O of 1, and this is a P2 with O of 2, and maybe this is a blow up of P2 at one point, which is F1. Oh, this was the original P2, and now it's a blow up. You blow up. Yeah, better P2. Yeah. So better say P2. So there is this little dictionary between toric geometry and combinatorics of polytopes. So anything about polarized toric varieties is just a statement about some combinatorial statement. Now, what about singularities? So especially the singularities we care about in minimal model program. Okay, so what's the canonical class of a toric variety? What do we know? First of all, on a toric variety, there is a boundary delta. Toric variety, there is a torus acting on it. And then there is the boundary is the complement. And this boundary just corresponds to boundary of this polytope. So for this variety, the boundary consists of 4 irreducible divisors. They just literally just correspond to this. It's boundary of the toric variety. And this is sort of the interior of the toric variety. That's the boundary. But it translates to this boundary is a union of toric varieties. Each of them corresponds to, of codimension 1, corresponds to a facet of that polytope. And here's the main theorem that this is 0. So k plus delta is 0. That's one thing we know from toric geometry. Now let's say to define these singularities we needed a resolution, and for a toric variety there is always a toric resolution which comes from toric geometry, from subdividing the fan, etc. And let's apply this thing. Let's run that definition for this resolution. So we have to pull back, say kx plus delta. I would like to know what are the singularities of the pair x delta. So I have to pull back 0. Pull back of 0 is 0. And so this is ky plus the boundary of y. And the boundary of y will be, there will be old boundary, and then there will be new boundary, also with coefficient 1. So as you can see, this pair x delta is log canonical. And it's essentially for free. So nothing happened, and then suddenly we proved something. And so you can say that you're very lucky, but of course there is no such luck, no such thing as luck. There are just deep connections between different fields of mathematics. In this case, between moduli, birational geometry, and toric geometry. But that's the connection for toric varieties.
As long as x is toric and the triangle is the boundary of x, you always get log canonical.
So for any project, for any toric variety whatsoever,
Yeah,
this pair x plus the boundary is always log
you
canonical.
still need the resolution to preserve the fan structure.
You need toric resolution, right? So you need equivariant resolution. So there is always such. This toric variety corresponds to a fan,
No, I know there is.
and there is always subdivision of the fan. That resolution is toric. So that map preserves the T action. So that's the y I use here. But one exists, even in any characteristic, even in characteristic P, still exists. So this pair is always log canonical, even in characteristic P. Now, what about the SLC pairs? So what can we do about that? All right, well, just as easy. Let's say you have several polytopes now. So maybe you have a big polytope, and now it's a union of 2 polytopes. So you sort of have a little glue in here. Now, of this you can to this you can associate a variety X, which is a union of two toric varieties. So these are toric varieties. They're glued along X12. And so X12 here is this, this boundary between them. And so how do you glue varieties? There is a standard construction. If you have two varieties and you have a common subvariety and it's a closed embedding, then you can glue. And this gluing will be, it's the direct limit of this diagram. You can do it in terms of rings. So in terms of rings, there's OX1, OX2, there's OX12, and there are surjections. And then you take the inverse limit of this diagram. And this limit exists. So it's easy to construct. For the rings, if there was R1 and R2 and R12, then this limit, it's a subring in R1 cross R2, a subring of pairs which have the same image there. That's all it is. So please note that this is exactly opposite to tensor product and fiber product. So the tensor product goes the other way. And so this is not the tensor product. This is this ring has zero divisors, always. And so the ring here will have zero divisors. Okay. So there is this simple gluing construction, what's natural to do is to call these stable toric varieties. And now the statement is that if X is a stable toric variety, then X with the external boundary this pair is SLC, and Kx plus this external boundary is 0.
I don't know if I understood your definition of stable toric variety. Are you only gluing along codimension 1 faces? Or can you glue along anything?
Yeah, you can do by anything. Right, you can start with a picture like this, say, and sure, you can glue those things. Then, all right. Then let me say, if the subdivision union of Qi is nice. I'll give you an example of nice. The support of Q is homeomorphic to a disk. This is nice. So, for example, if you started with a polytope and subdivided, then it has to be topologically Cohen-Macaulay. So there is a notion of topological Cohen-Macaulay just for pictures like this. And this picture is topologically not S2. And this translates literally to the condition that this variety is not S2. If it's homeomorphic to a disk, then this is topologically Cohen-Macaulay. And then this is Stanley-Reisner theory, slightly generalized.
Do all your pictures stay in the plane, or can I, have the boundary of the ball as my...
Exactly, you can do anything. What they have to be, they have to have a map to this Z to the R. So each polytope has to map isomorphically to some polytope. But then when you glue, it could be, for example, it could be 2 copies of a triangle. And it's a 2-to-1 map. And then they're only glued along the boundary. So I do that general case, but then in applications, really, this is pretty much the only case needed. And let's stick to that. Let's not complicate anything. So let's look at simple subdivisions of polytopes, and then I don't have to say.
Stable just means that the gluing comes caused by the detailed picture.
I'm sort of defining them explicitly.
Yeah.
That's what I'm doing. I could also give an intrinsic definition, but maybe it will scare you a little. But stable is an overused name. It all just brings back the memories of stable curves, of stable Deligne-Mumford curves. So since Deligne-Mumford, any kind of varieties appearing in compact moduli, you tend to call them stable. So.
I don't understand your answer to the rest of it. So you're saying that those are stable but don't appear in moduli space?
These don't appear as limits of normal toric varieties.
So why do you call them stable? I mean, so they're not in that moduli.
Yeah, I'm sorry, I just did. So it's too late to change. So. Okay, so our general prediction is that now there should be a moduli of such things, except I don't know if you noticed, but so far it doesn't really fit the picture yet. So in that definition, k plus b was ample, and right now k plus b is 0, and so you have to do something to have k plus b ample. And have to modify this a little bit. So here's the modification. What you should add to the picture, you should consider S a section of the sample line bundle, and take the divisor, which is the 0 of that section, and look at the pair not kx plus boundary, but add this divisor d with a very small coefficient, with some epsilon. And now this is ample, right? So what I'm adding here, here I'm adding a line, right? This is a tropical picture for a line. And adding some kind of divisor here. So for any divisor whatsoever in here, if you added with the epsilon coefficient, then this was 0. Now it's ample. But there is a condition that this pair has to have log canonical singularities in this case. So what is that condition equivalent to? So the pair x delta plus epsilon d is log canonical in this case. That means that this new divisor does not contain any centers of log canonical singularities for that pair. There are already some parts where the singularities are maxed out. You cannot make them worse. And these parts precisely correspond to toric orbits. So they correspond to all the faces of all dimensions in the polytopes. And so this is equivalent just saying to D does not contain any T orbits. So really does not contain the vertices. In this toric variety, you have finitely many torus fixed points, and this divisor should not contain them. And then that's the condition on singularities that you have. So now, so same for stable case. So now we have a prediction that there should be a moduli, And it's really fortunate that we added this divisor, because without the divisor, there was no moduli. There is only one toric variety. For a given polytope, there is only one, up to an isomorphism, there is only one toric variety. And it has an infinite automorphism group. So there is a toric stack. There is a stack which looks like this, 1 over torus. But it's only one isomorphism class and infinitely many automorphisms. Now, once we added the divisor, then immediately the automorphism group becomes finite of this pair. And we have a moduli. And what is the dimension of the moduli? So dimension of the moduli of these pairs x delta plus epsilon d. So we have dimension of L. That's where the section lives. It's only up to a multiple, so -1. It's an element in the projective case. But in a toric variety, you have an origin fixed. And in this picture, I don't have an origin fixed. So I don't care where the origin is. So so that's the dimension. And in the combinatorial language, I'm counting the integral points, and then subtracting this number. So that's the dimension of the moduli. Okay, now we got the singularities for free. Now let me tell you that we also have degenerations for free. There is this general construction. It's complicated, uses minimal model program. For toric varieties, there is an easy construction, which uses hardly anything. So let's do that. So I will start with some polytopes. For example, this is the polytope. And then start with a height function. And a height function is a function on the integral points with values in z. So I should draw that as some heights. So for all of these points, there is some height function. There are values. And let's look at the polytope Q tilde, and this will be the convex hull of the points V, H of V. V are all the integral points, and also of the points V and some minus n. Some large number n. I'm going to, in the end, it will not matter, but I just want something. So let's look at this convex hull, and for example, it looks like this. I missed. Okay, this part will not matter. There. Okay, so there is a toric variety, right, corresponding to this polytope, and this toric variety comes with a map to P1. And if you played with this a little bit, then you know how it works. So what the fibers are, and the fibers are, if you take a t in here, and if t is not 0 or infinity, then the fiber is a toric variety, your original toric variety, x cube. That's what it is. So all those fibers are like this. And the fiber over 0 is, now it's a stable toric variety for the roof. So there's a roof and the bottom I arranged conveniently. I don't care about the bottom anyway. So let's look at the roof, and So what you have there, you have several polytopes that if you project, they will project to a subdivision of your polytope, of your original polytope. So there is a stable toric variety corresponding to that. And that's what the central fiber is. Right? You take a convex hull, and then there is this roof. It's no longer straight. It kind of it got broken up somehow in a convex way. So the subdivision is it corresponds to a convex subdivision. So in this case, it's this. So in this concrete case, here's all that happened. There is this toric variety, which is a quadric in P3, and you can degenerate it to this variety, which is a union of two P2s, or you can degenerate it to this variety, which is also a union of P2s in a different way. So that's all. And now all I'm saying is that you can do it always.
So what's the polytope of P1 so that you actually get to that?
Say again? Oh, the polytope, polytope of P1 is an interval. Now, to be completely honest, here's the point where difference between nice polytopes and nice cones and horrible semigroups, not saturated semigroups, comes to play. So if I do just this, the fiber could be non-reduced. So if you just do it what I just did, the fiber is in general not reduced. But if you make a finite base change, then it will become reduced and will be a stable toric variety. So this is after a finite base change of this form. So this finite base change makes some semigroups to be saturated, and then it's true. All right. So we're getting to some combinatorics. Uh-huh.
Are you saying it actually gives you a family of toric varieties over P1? Or is,
Say again?
are you saying you actually get a family of toric varieties?
Yes, it's a family, right. It's a family over P1 minus 0 and infinity. You have a family of toric varieties. It's a trivial family. Trivial family. All the fibers are isomorphic. And then there is this degeneration, right? And this degeneration is a stable toric variety. Now, so what's puzzling, I'm guessing, so what's puzzling to you is that there was a trivial family but a non-trivial degeneration somehow. Okay, number one. Number two, there are lots of height functions. So there are sort of many of these degenerations. That's because we haven't added that divisor D yet. That's why this is happening. So once you add this divisor D, then the whole picture becomes regularized. So let's do it. Now let's have a family of divisors dt. So each of them is given by a section. This section now will be a function of t, and that section S. That section S in the fixed picture, it was it can be written as a sum of monomials. Monomials go over the integral points in this polytope. So for a P2, there are the monomials are x0, x1, x2, but etc. So for any toric variety, there are these monomials. So if you do it in a family, then S of t will be, these coefficients will depend on t. Now, let's look for a limit of the pair now. So I want not just the limit of toric varieties, but I want this limit of these to be somehow nice. And so there are conditions, first of all, that on this fiber S of 0, well, so on the whole family, S has to be regular. And that translates into the following. That translates into the condition that the valuation of the Cm of t valuation is just, you write this as a power series and you just look at the first non-zero term. So this has to be at least h of n. H is the height function. Because in the family, these are the leading monomials that give us the regular functions. And then, but we had a stronger condition, that this condition. So S of 0 does not contain any t orbits. That's equivalent to saying that the valuation has to be precisely h of n. So for any m, which is one of these vertices of these polytopes. So don't have time to explain more, but this is a very easy argument. If this valuation is strictly bigger, then that coefficient just becomes 0. And then that divisor will contain the corresponding vertex, so the corresponding fixed t orbit of a toric variety. But what's the conclusion from this? The conclusion from this is that this family dt dictates the function h, the height function h. So there are infinitely many choices for h. But if you want this limit as a pair, and you want the limiting pair to have SLC singularities, then there is only one choice for a height function, and it's this one. So this is how the two things join. For a pair, there's a unique choice, and that unique choice has SLC singularities as predicted by the minimal model program. I am quickly running out of time because I'm still on 2, right? Just somewhere maybe in the beginning of 3. So some sacrifices will have to be made, but something I still want to say today. Before stating some general theorems and stuff, let me point out this connection with combinatorics which appeared in the work of Gelfand, Kapranov, Zelodinsky. So here's what you do. So you look at the vector space, of all height functions. Okay. So that's how big is this vector space? It has there is one variable for each integral point, so that many. And you map that that space. Just there is a set theoretic map to a subdivision of Q given by the roof, just as I did, right? So there are only finitely many answers here. So this set, this is a finite set. So there are finitely many elements here. So all this vector space is subdivided into finitely many subsets. Now, some functions do not matter, and linear functions do not matter. If you have a linear function, the roof is flat, right? Or if you add a linear function, your subdivision will not change. So now this quotient space has the dimension. Maybe you can see what the dimension that it matches. So on this vector space, you have a subdivision, and this subdivision, so you get a subdivision. This subdivision is a fan. It's a fan. It divides into finitely many convex, finitely generated cones. And it's called a secondary fan. And so for this secondary fan, there is what's called a secondary toric variety. So X, secondary fan, sigma, and so X sigma. And moreover, this secondary toric variety is projective and polarized. And it corresponds to the secondary polytope. Delta of Q. And it has this dimension. So there is this nice construction which predates all these stable toric varieties. Now, maybe I'll state the theorem, and then think for a second what to do next. So the theorem is that for every Q in this polytope, there is a moduli space MQ, M bar Q of stable toric pairs of type Q. And of type Q means that they correspond either to Q or to subdivisions of Q. So like that. And this modular space doesn't have to be irreducible, but it has the main irreducible component. It's the one that contains normal varieties. So the main irreducible component, if you take the normalization of it, then this is the stable, this is the secondary toric variety X delta of Q. And if you look at other irreducible varieties, components, and again, it's up to normalization, then there is some notion, which I defined, some generalized, okay, it's toric varieties. There are again toric varieties for generalized secondary polytopes. So all irreducible components have a description similar to that. Just you have to generalize that secondary polytope a little bit. And so when do these appear? So these appear when when there exist non-convex subdivisions of Q. You see, the one-parameter limits, the one-parameter degenerations, they always correspond to convex subdivisions. Now, so if you can think of some non-convex subdivision, then automatically it does not appear as a limit. So automatically it will not be in the closure of the main component. So it will have to lie in some other components. And the simplest sort of 101 example is this. This is the simplest example of a subdivision which is not convex. And it's not very original, but I called it an Escherian staircase. Because it's a picture of a staircase which always goes up. Right? And that cannot be a three-dimensional picture. There is nothing three-dimensional that looks like this. Okay, so decision time. The decision is to stop here. And I'll try to kind of say, finish 3 and maybe say a little bit about 4 next time. I think that's reasonable.